So David Hensle with RSG is going to be presenting on an example DTA application from Michigan using DTA for Ford Motors Corktown demand responsive transit simulation. And David is in his third year with RSG as a transportation modeling analyst. His primary focus is on travel demand forecasting and has contributed to the development of many travel demand models, including the Detroit, San Francisco Bay Area, and San Diego. He's also an active software developer on the Activity Sim activity-based modeling platform, and he comes to us with a background in physics. So David, I'll go ahead and let you take it from here.
Thanks, Randy. So you guys should all be able to see my screen. I guess holler at me if you don't see it. But we're talking today about our work with Ford Motors on a demand responsive transit simulation in Wayne County, Michigan, which is the county that surrounds Detroit. So kind of where we're going here, we used MatSim to simulate traffic in the greater Detroit area. So I'll walk us through some background, a little bit on the MatSim tool in general, what we did to develop the network and put some demand on there, and then the modeling of this demand responsive transit, which is essentially like an Uber pool service, but with kind of an eye towards automated vehicles. So project background, it was a collaborative effort between RSG and ETH Zurich. ETH Zurich is one of the primary developers and users of MatSim, so we leaned on them a lot for MatSim specific knowledge, and RSG was primarily responsible for a lot of the network and demand development. So the project essentially started with this new, or I guess old building in the Corktown region of Detroit, just outside of downtown Detroit. Ford Motors bought this historic building, the Central Michigan Station, a couple of years ago, and the idea was that they're going to turn this kind of decrepit old historic train station that used to be kind of the jewel of the community in this area, but that has since been run down, into a brand new office focusing on autonomous vehicles and all of Ford kind of administrative offices. So that's kind of the idea here, is that they wanted to understand what the impact of adding 5,000 workers or something like that to this area and how it would impact the traffic around the region. And not only that, but explore different and new mobility options like this Uber pooling type service, but with an eye, like I said, towards more autonomous vehicles and ride sharing options. Fun fact, this is also the building where this fight scene from Batman versus Superman happened. So if you ever watch that movie, and you see them fighting in some old decrepit station, it's actually this building that Ford is currently remodeling. So I'm going to talk a little bit about MatSim, kind of what it is. It's a DTA model. MatSim stands for Multi-Agent Transport Simulation. It's an open source application written in Java, and it just simulates the flow of traffic and congestion based on the daily schedule of individual synthetic travelers, or agents in this case. MatSim, it applies an iterative co-evolutionary approach to maximize the utility of each traveler's day. So that's kind of given by this MatSim loop here, where you start with some scenario data. So each individual person's plans, the individual network links and architecture of the network. And then you kind of route each one of the agents on the network. There's a lot of parallelization and computational optimization that happens here to get everybody to go where they're going. And then there's some scoring function that determines how quickly or how well an agent goes from their origin to their destination. Generally, MatSim has the ability to change people's daily patterns to try to reach convergence with a kind of co-evolutionary approach. We didn't really want to allow people to change where they were going or when they were going there. We did allow people to change the route, how they got there, and the mode, what they used to get there. So there's kind of a scoring function, which we limited in this instance, and then there's this replanning kind of loop that comes back, and you kind of run this until you reach some convergence. And then, of course, we want to do output analysis like traffic volumes and mode choice distribution, things like that. So MatSim, it really works on a link level. So you'll have individual agents, but you don't necessarily track the vehicles individually within the link. So it's a link queuing model. So it's kind of a mesoscopic approach here, and that's just to be able to model larger regions in the computational time that's reasonable. So kind of an overflow or workflow diagram, I guess, of what kind of goes into this whole thing. And we'll kind of talk about each one of these pieces here as we go through the rest of the presentation. But you'll have a network. We got ours from OpenStreetMap. We also included some transit data in here. We used the region strip-based model as our demand, and we assigned them to the network. And then we fed MatSim in, fed this all into MatSim. And I guess when I say assign trips to network here, I mean starting and ending links on the network. And then we allowed them to be simulated by MatSim, right? And there's a mode choice model where we added this DRT option, and then we'll have some output analysis, and then this process kind of gets iterated as a function of how we're doing. So moving on to the demand and network creation. So the demand, as I just mentioned, came from the region's trip-based travel demand model, the Southeast Michigan Council of Governments, which is the MPO for this big 7-county or whatever region that they have here. There's almost 3,000 TAZs in this area, corresponding to 21 million person trips. We were really only concerned about this Wayne County modeling region here. So that essentially trimmed it down to only about 11.7 million individual MatSim agents. And we distributed them temporally and spatially from the SimCap trip-based model onto our MatSim network. I think it's important to kind of note here that we use the SimCog travel demand model because it's already a calibrated and validated model. We didn't really want to necessarily, try to create a travel demand model from scratch for this whole project. So the idea is to use something that's already been created and used and validated. And the idea is also that it could be a little bit more easily replicable to other regions that have similar trip-based models. So the network, OpenStreetMap, if you haven't heard of it, is just an online database that contains all the streets. So there's a open source Python package called OSMNX that we use to extract the network. And you can see, right, we just kind of drew this polygon and then used this Python package to extract it from the database. And we ended up with approximately 236,000 individual links here, which is a lot. So what we did was we wanted to trim the network so to help our computational time. We did want the detail in downtown around the Corktown campus, which is like kind of right here. This is downtown Detroit. The main area is here, but of course you'll have people coming, moving all over the really dense metro region here. And then what we did was we took the SimCog planning level network and we trimmed out all the kind of auxiliary streets outside of the downtown region. to avoid unnecessary computation time. There's a lot in here that can be really tricky when we're talking about network cleaning. So here's an interesting case where we trimmed the network, right? This is kind of a smaller road, but these were more of main arterials. And so this just happened to be kind of on the line that was cut off. But this actually created a routing problem. So even though the roads are correct here, because we trimmed this out, there's now a routing problem because this is a one-way segment and this is a one-way segment. So if you have any agents that try to start on either one of these links, when you distribute your agents onto the network, then they're not allowed, there's no way for them to route out of this segment. So it's like things like this that can be very tricky when you're dealing with a large scale region with a lot of network links. We also included some transit. So there's a Java application called PT to MatSim, which takes the GTFS data for this region and integrates it with MatSim network. So you can kind of see the coverage. Detroit doesn't have a whole lot of transit in it. There's one Q line here, which is a streetcar that kind of runs on one street in downtown. There's a central business district circulator here called the Detroit People Mover. And then there's this bus system, and then there's a few more bus routes that kind of extend out into the suburb region. So you can see this is what it kind of looks like when you load it up in MatSim. We have a really dense network in the downtown region, and then a planning level network around it. And then when we include transit, it'll include extra links in here. And so you see that, as I said, it really extends out in the suburbs, and that's what all these extra links are up here, is the bus network that extended beyond our model region. So to kind of summarize here, right, we started with OpenStreetMap for the Wayne County. We trimmed it. We added some transit to the network, and then converted it into a MatSim format. And we were able to do all of this with open source data and open source tools, which I think is pretty cool. So now we have a network and the demand on here, we can actually kind of load it up. And so I'm playing this little video showing, if I zoom in here, the individual MatSim agents that are going around on the network. And you can kind of see, if you kind of look in this region, there's a link that gets congested. And so that's like the link level queuing that I was discussing at the very start that the MatSim kind of works on. So pretty mesmerizing to kind of watch this for a little while. You can kind of see that there's portions around here in the network in this video that are more congested than others. And so what you can kind of do with this, if I kind of move on and take kind of snapshots throughout the day, is you can kind of see where the problem spots are on your network. So here's your volume at 8 a.m. There's a big freeway interchange right here. There's a freeway coming this way and a freeway coming down. And as you kind of zoom through the day, 8 a.m. to 10 a.m., it grows. And then 1:30, it really grows. And then by the time you're in the PM peak period, it's really spread, and it doesn't get any better by the time 6 o'clock rolls around. So what this really leads us to is there's generally regions in your development cycle where you have network problems. So for example, there's this interchange right here. There's 8 Mile Road and I-75. And there's this little link, like this one right here is a link in the network. And in reality, it's 2 lanes, kind of this split lane deal, but it was coded as 1 lane from OpenStreetMap. So here's an example where people are coming off the highway or trying to get on the highway, and this one small tiny little lane backs up, which causes a backup onto the highway, and it just spreads throughout the day. So very small problems in your network can really cause headaches and when you're doing scales like this. So after we kind of sorted out a bunch of those issues, we were able to look more at the demand responsive transit portion. And the way that we incorporated this was by using a mode choice model. So we have our usual car mode, some non-motorized modes, and public transit. And then we added an additional demand responsive transit mode here. The parameters for this mode choice model came from the SimCog trip-based model. They include things like in-vehicle time, out-of-vehicle time if you're doing things like walk to transit, or walking or biking. We also have some travel costs, auto operating costs or toll costs. We have utility terms based on the household income and the availability of a vehicle for the household from which that agent comes from. And so what you essentially get is for each person, you'll have, you sum up all the utility terms, and then you create a probability from that. And then you randomly draw from that probability distribution for each person to be able to have some people that select demand responsive transit. And also some elasticities based on travel cost or whatever parameters that you have in your model, and that will change. As you change those, that'll change the probability that people will select your given mode. So the way that the demand responsive transit simulation really worked here was that an agent would go through the mode choice, they would see some travel costs, and they would pick the demand responsive transit mode, and this submits a request to what we're calling the centralized dispatching system. And then this is responsible essentially for telling which DRT vehicle is going to be able to pick up this agent, if any, right? So in some cases, there's no really available vehicle that's within range of the agent, and in which case they might get rejected. So like I say here, dispatch algorithm calculates the detour time based on the maximum detour time and the wait time. So it already knows where that vehicle is going when the request gets submitted. And then it just assigns the vehicle with the smallest detour time for pickup and drop off. So we tried a bunch of different scenarios. We tried multiple different fleets, multiple different vehicle occupancies, the size of the DRT vehicle, and 2 different fares, $2 and $4 fare, just a flat fare. We didn't do any distance scaling here. And we fixed sometimes here, we said that the customer was only allowed to wait 15 minutes. If they had to wait for more than 15 minutes, then their request was rejected. If there was more than a 15-minute detour time for the vehicle, then that vehicle is not allowed to pick them up or drop them off. And then there was an additional almost 2-minute wait time at each one of the stops that was included. And so as we go through our simulations, so kind of talking through these plots here, this is the number of travelers, or the number of agents, the number of people who requested rides, the number of vehicles in the fleet, and then there's 2 colors. The $2 fare is the blue one, and the $4 fare is the green, the gray one. The lines up here are the total requests. So for a fleet of 100 vehicles, you see, there's 35,000 requests, but only 5,000 people actually got served. So the rejection rate is extremely high. If we double the fare, then the number of requests goes way down. There's been a lot fewer people who are willing to pay $4 than $2 to take this service, but we still have a rejection rate of 1/3 or something like that. I guess 2/3 being rejected. And so you can kind of see that these go through this plot is essentially the inverse of this one. But as you get to higher fleet sizes, you have 1,000 vehicles, you're still not really able to serve all the rides. So a large portion of rides were rejected. That's kind of a function of the size of the area that we were working with, right? Wayne County and Detroit is pretty large. And so there's a lot of area to cover. And so even with a large fleet size, 1,000 vehicles, we're still rejecting people, and we're still having vehicles that are not being used all the time, right? Because they just don't have somebody within 15 minutes that they can pick up or drop off. And also as a function of this low density in the Wayne County region is that the occupancy for these vehicle rides was pretty low. So you can see the amount of deadheading of these vehicles here. And most of the passenger distance is with one passenger in the vehicle, and very small amount of ride sharing with two, or 4 is pretty much non-existent. There's a couple cases where we have a couple vehicles that had up to 3 people in them. We also took a look at wait time. So the average wait time of the fleet, it's not very sensitive to fare. It is, of course, sensitive to the size of the fleet, as you would imagine. As the size of the fleet goes down, the wait time goes up because the density of vehicles on the network that can pick and drop you off decreases. So to kind of summarize here, most of the DR trips ridership comes from the car mode share. So that's where we saw a huge shift, was people switching from car to this DRT mode. That's probably not surprising, considering most of the people that are in the Detroit region use car anyways. It's a very low transit share area. The county's relatively low density leads to a very low potential for ride sharing. You could think of scenarios where you would restrict this service maybe to just the downtown region, in which case you might see a better vehicle utilization. The fleet might be a little more active, but then you're, of course, decreasing the size of the share of people that could possibly use the service. We found that increasing the fare from $2 to $4 was very sensitive for the number of people that were riding. It was almost 1-to-1, so a decrease in fare by a factor of 2 essentially took away half of the riders. We worked on the average wait time, how that's affected by fleet size. Network congestion is also an issue here, of course, as is like the number of rejections. As you have a lot of network congestion, right? If our DTA model is not very well calibrated, or if we have errors in there that's leading to congestion based on network problems, it kind of throws off a lot of this stuff. Some limitations and kind of some future direction is there's a lot of parameters to play around in this space, especially with the DRT service and mode choice and kind of the assumptions that might go in there. It would be really cool to use the demand from a tour-based instead of trip-based model, and be able to kind of feed this back into a regional travel model to have, you know, more accurate changes based on the mode shares that we were seeing. Run times for this model were very long. It took multiple days for us to do that MatSim loop iteration and converge to a solution. And some other, I guess, some general takeaways I have on here. As you kind of saw, and the point I tried to make here was that network accuracy is very important for DTA. But DTA also provides really the unique ability for us to visually see the routing and spacing, especially of a shared fleet like this, where static assignment doesn't really do, you know, routing of vehicles on the network. So if you want to understand what your fleet is doing at any given time, you kind of need a tool that does that. All of this can be seen in a TRB paper that we wrote as part of this work, if you're interested. So I think I'm like right on time. That was my last slide. Any other questions for me?
Yeah, perfect, David. Thanks for helping us keep on time here. So yeah, there are a handful of questions in the chat. I don't know if you want to
Let's see.
dig up those yourself, or if you want, I could read them for you.
Yeah, I can't find the chat box button, so maybe if you can just
Okay,
read them for
sure.
me.
So Alex Benardi is asking the first question here with, does MatSim provide a way to calculate an optimum size fleet for the demand?
Not really out of the box. You might be able to like cheese it somehow. I guess my answer here is no, but you could maybe do it with some really clever thinking.
Yeah, that would certainly be a pretty helpful tool to have. Okay, next question up is from Chayton. Is the dispatching algorithm part of MatSim or external tool? Any more details available on that?
It's an extension of MatSim, I guess is the best way to put it. So MatSim, you can go find it's an open source tool as well. So you can go look at the repository that they have. I don't think it's part of the official release. It might have been pulled in recently. Part of this demand responsive transit, I think was, an extension, but I think the work was being done to pull it in, and it might be in there right now, more integrated.
Gotcha. And Alex has another good question here. Is deadheaded included in the congestion calculation? Are those vehicle trips in the assignment?
Yeah, yes. So you saw, right, this, these distances for deadheading, MatSim output actually includes like full vehicle routes. And so you can kind of extract exactly where each individual vehicle goes on the network. And from that, you can calculate distances on an individual vehicle level. So that's how these plots were created. We essentially grabbed those vehicles on the network that were doing this DTA, and we just calculated from their whole day and what the vehicle occupancy was to calculate deadheading. And also because in the simulation, they're included in there, so they also contribute to congestion. But the number of vehicles is pretty small, so it's not like they had a major impact.
Gotcha. All right. And another one in here from Alex. I probably missed a slide, but how much variation was tested in paying for the ride versus the cost of ownership / operation?
Paying for a ride, meaning on the DTA versus the cost of owning a vehicle, or the cost of operating the vehicle itself?
Yeah, sorry, I wasn't sure how to type that question quickly. Basically, was there variation in how attractive it was to take this mode versus owning your car? Like, how much sensitivity was testing around? Well, like if it's free, I'm gonna that's clear. I don't know.
Yeah, so that was kind of the point that I was making about it'd be cool to integrate this with a the regional travel demand model. If this becomes a mode and it's more available and people are willing to take it, does that mean that less people are going to own cars? That's not something that was explored as part of this project. If that's answers your question.
Sure, but was the demand, that makes sense. So the ownership is somewhat static, but was the amount of shifting to this new mode function of, was there a variable tested in how much the ride cost the chooser?
Yeah, right. So that's this fare cost here. And so if you look at the mode choice model, this travel cost, the fare would come into this travel cost if you're in the demand responsive transit portion, right? Or if you're in public transit, it'd be the fare of the transit vehicle. Or if you're in a car, we have some auto operating cost parameter that comes in there as well.
Got it. Thanks. I just missed the slide. Thanks so much.
Okay, and then final question here before we jump to the next presentation from Peter Bosa. Did you validate the MatSim all-day network results with observable data?
Yeah, so we took the counts that were from the SimCog model, or so the SimCog region, and we linked them onto the network, and we did some count analysis as a function of time of day. That was kind of the main validation plots that we used, and we also wanted to make sure that the mode choice model was validated as well based on the mode shares in the SimCap region. And in
just
in the model.
just a quick follow-up, David. Thank you for answering that. Did you have to do some sort of like demand adjustment for MatSim? I mean, or did you find that putting in the raw demand from the SimCap model, you were able to match, you validate pretty well against the counts?
Yeah, I mean, that's a great question. I think the counts themselves, matching the counts was more about the level of congestion, which had more to do with the network cleaning. In terms of the demand, I don't think I have a slide in here talking about the demand a whole lot, but this was tricky because, right, the trip-based model has very defined time of day periods. And if we want to be completely consistent with the trip-based model, which we did, I mean, we wanted to kind of stay with that. There's these discontinuities that happen at these time of day periods where, like from the midday period to the PM peak period, for example, you have kind of this spike in demand. And even if we kind of distribute people in a way that makes sense temporally on the network, you still have this kind of discontinuity because there's a whole lot more people that kind of show up on the network at 4 p.m. So that was a challenge for us, and it wasn't necessarily really resolved. So if you were to look at individual like half-hour time periods on the network, the validation might not look as great as if you were to look kind of at the whole day.
Okay, perfect. Well, thanks again. We're going to go ahead and jump on to the next presentation, which myself and my colleague Caleb Huskies will be taking the reins here.